This is my fifth video lesson for the covalent bond unit. In this lesson, we'll be analyzing the Lewis dot diagrams of covalent compounds. So let's go to page 16 in the class packet. For motivation, I want you to draw the following Lewis dot structures. So take a moment to do that. The first compound is NaCl. It has a metal and a nonmetal, so it is an ionic compound. The second one is NaOH. If you recall from the previous lesson, OH is a polyatomic ion, so NaOH has both ionic and covalent bonding. CH4 is all nonmetals, therefore it is a covalent compound. If you look at CH3OH, it has all nonmetals, but it seems to have a polyatomic ion, hydroxide. So is CH3OH only covalent or both ionic and covalent? So, which is correct? So here I drew two versions of the Lewis dot diagram of CH3OH. This one has ionic and covalent bonding. This one is only covalent bonding. So students typically get confused and they either draw this one or draw this one. So it turns out this one is the correct one. It only has covalent bonding. So how can we tell? By just looking at the chemical formula. I'll show you in this lesson. Learning target. At the end of the lesson, I'll be able to identify if a substance has ionic or covalent bond or both, and analyze the structure of covalent compounds with formal charge and resonance. So homework will be number 5, which will be a journal pod based off this lesson. Let's first review the term non-binary. So non-binary means 3 or more different elements. So from the motivation, which was non-binary? Only NaOH and CH3OH were non-binary because they have 3 different elements. So be careful with substances with polyatomic ions because they can have both ionic and covalent bonds. Question number 1, what type of bonds exist in a polyatomic ion, ionic or covalent? So just to review, a polyatomic ion has covalent bonds. So if we look at nitrate, nitrate has covalent bonds. The nitrogen and oxygen are bonded covalently, but because nitrate has a charge, it can ionic bond with the opposite charge ion. For example, in calcium nitrate, the nitrate ion is ionically bonding with the calcium ion. So the question is, how do we know if a chemical formula has a polyatomic ion? Just because you see the same elements in the chemical formula does not necessarily mean it has a polyatomic ion in the compound. I will go over a procedure in figuring out if a compound has a polyatomic ion or not. Your first step is to look at the chemical formula to see if there might be a polyatomic ion present using table E. So in our example, we have C2H5OH. It might have a polyatomic ion OH, which is hydroxide. The next step is to check if both components are ions. In order for there to be an ionic bond, you need both a positive and a negative ion. So if OH is a hydroxide ion, which is negative, then C2H5 must be the opposite charge. So the question is C2H5 an ion or a polyatomic ion? If we look on table E, C2H5 is not there. Therefore, it is not a polyatomic ion. If that's the case, then OH is not hydroxide ion in this case. So if both are not ion, then there is no polyatomic ion. Therefore, your compound only has covalent bonds. Only if they're both ions is there a polyatomic ion. Therefore, your compound has both ionic and covalent bonds. If you were to draw the Lewis dot diagram of C2H5OH, it will look like this. So this is only showing covalent bonding. There is no ionic bond or polyatomic ion present. Let's do another example. Let's look at KOH. Our first step is to look at the chemical formula to see if there might be a polyatomic ion present. By looking at table E, OH might be hydroxide ion. Our next step is to check if both components are ions. So the other component is K. So is K a positive ion? The answer is yes. K is a metal, and metal form positive ions. And since both are ions, then there is a polyatomic ion. And if you draw the Lewis dot diagram, there's both ionic and covalent bonding. Learning check number 1. NH4Br has what type of bonding? Pause the video and resume once you complete it. So this is a tricky question because NH4Br, these are all nonmetals. But it does not mean it's all covalent bonding because this is a non-binary compound. So there might be a polyatomic ion. If you look at table E, you'll see that NH4 is a polyatomic ion, ammonium, which has a charge of positive 1. So the question is, does Br have a charge of negative 1? If you look at the periodic table, Br is a nonmetal, and Br can have a charge of negative 1. And since both parts or both components are ions, then it has both ionic and covalent bonding. So the answer is choice 3. And this will be the Lewis dot diagram of NH4Br. So you can see it has covalent bonding and ionic bonding. Learning check number 2. Which compound has both ionic and covalent bonding? Pause the video and resume once you complete it. So in this question, you're looking for a polyatomic ion in the compound. So only choice 1 and choice 3 might have a polyatomic ion. Choice 2 and 4 do not, based off of table E. Choice 1 has CO3, which is carbonate ion. Carbonate ion has a -2 charge. So the question is, does calcium have a positive 2 charge? If you look at the periodic table, calcium is a metal and it has a positive 2 charge. So this has both ionic and covalent bonding. If you look at choice 3, it might have a polyatomic ion hydroxide, which is a -1 charge. So the question is CH3 a positive 1 charge? If you look at table E, CH3 is not a polyatomic ion. Therefore, CH3OH only has covalent bonding. So the answer is choice 1. Learning check number 3. Which compound contains both ionic and covalent bonds? Pause the video and resume once you complete it. So the answer is choice 3. Why? Because sodium nitrate has a polyatomic ion, nitrate. But for the next practice, I want you to organize the following compounds as ionic, covalent, or both ionic and covalent. Pause the video and resume once you complete it. Okay, so here's the answers. So if a compound is only ionic, it's only between a metal and a nonmetal. For covalent, these are all nonmetals. And for both, these compounds have polyatomic ions. So as long as you follow my procedure, you should be able to get this correct. For the next practice, I want you to draw the Lewis dot diagrams of the following compounds with both ionic and covalent bonds. So pause the video and resume once you complete it. Okay, so here's the answers. In the second part of this video lesson, I'll be talking about formal charge. Formal charge is a charge assigned to an atom in a molecule. The assumption is electrons in all chemical bonds are shared equally between atoms, regardless of the electronegativity. There are 3 reasons why we assign formal charges to atoms. The first reason is to figure out the best Lewis dot diagram amongst many possible Lewis dot diagrams of your molecule. The best choice is often the one with the most neutral charges. The second reason is to help you envision where might be the regions of positive or negative charge in a molecule, which could be useful in understanding how a molecule might react in a chemical reaction. The third and final reason is to figure out if the overall charge of a molecule will be negative, positive, or neutral. So here's the equation of calculating the formal charge of each atom in a molecule. Formal charge is equal to the number of valence electrons in a neutral atom minus the covalent bonds minus the electrons in the lone pairs. So let's do an example. So let's look at oxygen first. How many valence electrons does a neutral atom of oxygen have? So oxygen has 6. How many bonds is oxygen forming right now? It's forming 2. How many electrons are in the lone pair? It has 1, 2, 3, 4. So now we plug this into the equation. 6 minus 2 minus 4 is 0. So the formal charge of oxygen in this molecule is 0. Now let's do the same thing for carbon. How many valence electrons in a neutral atom of carbon? Carbon has 4 valence electrons. How many bonds is this carbon forming? It's forming 1, 2, 3, 4. How many electrons are in the lone pairs? There is none for carbon. So 4 minus 0 is 0. So the formal charge of carbon is 0. Since this oxygen is equivalent to this oxygen, the formal charge of this oxygen is also 0. As you can see, the formal charge of each atom is 0, so the total charge of the molecule is also 0. Let's say you draw the Lewis dot diagram of CO2 like this. This Lewis dot diagram is also valid because each atom has fulfilled the octet rule. So which Lewis dot diagram of CO2 is better? Let's figure out the formal charges. This oxygen is 6 minus 1 minus 6. That is -1 formal charge. This carbon is 4 minus 0. That's 0. This oxygen will be 6 minus 3 minus 2. That's +1. The total charge of the molecule is still 0, but the first Lewis dot diagram is still better because it has more neutral charges compared to this Lewis dot diagram over here. So this one is the best Lewis dot diagram of carbon dioxide. Let's do another example. Here's the polyatomic ion NH4+. How many valence electrons are in a neutral atom of nitrogen? If we look at the periodic table, it is 5. How many bonds is this nitrogen forming? It's forming 1, 2, 3, 4. How many electrons are in the lone pair? There are none. So the formal charge of nitrogen is 1. 5 minus 4 minus 0 is 1. Now let's do the same thing for hydrogen. Each of these hydrogens are equivalent. How many valence electrons are in a neutral atom of hydrogen? It is 1. How many bonds is this hydrogen forming? It's forming 1 bond. How many electrons are in the lone pair? There are none. So the formal charge of this hydrogen is 0. 1 minus 1 minus 0 is 0. So let me label the formal charges of nitrogen and hydrogen. If we add up the formal charge of each atom in this molecule, it will be 1, which is the total charge of ammonium ion. Learning check number 4. What is the formal charge on carbon in a molecule below? Pause the video and resume once completed. So the answer is 0, choice 3. A neutral atom of carbon has 4 valence electrons. In this molecule, carbon is forming 4 bonds, and there is no lone pair electrons, so 4 minus 4 is 0. Learning check number 5. What is the formal charge on nitrogen in the structure below? Pause the video and resume once completed. So nitrogen has a valence electrons of 5. Currently is forming 4 bonds, and it has 0 electrons in the lone pair. So the formal charge of nitrogen is +1. So the answer is choice 4. Here I have 2 possible Lewis dot diagrams of SO2. Which one is the better Lewis dot diagram? Notice each Lewis dot diagram is following the octet rule, so they're both acceptable Lewis dot diagrams of SO2. Sometimes there could be many possible Lewis dot diagrams given the same substance. So one way to figure out the better Lewis dot diagram is to use formal charges. Your first step is to figure out the formal charge of each atom. So this oxygen will be 0, this sulfur will also be 0, and this oxygen is 0. Now for these atoms here, this oxygen is 0, this sulfur is +1, and this oxygen is -1. In both cases, the sum of the formal charges is 0, so both molecules are 0. These Lewis dot diagrams are resonance structures of each other. So which is the better Lewis dot diagram? So if you recall from previous slides, The better Lewis dot diagram is the one with the most neutral formal charges. That'll be this one on the left. So why are these not isomers? If you recall, isomers have the same chemical formula, but different structure in terms of arrangement of both atoms and electrons. If you look at these Lewis dot diagrams, their structures in terms of the atom placement is the same. They're placed in the same order, but they differ in the arrangement of the electrons. That's why they're called resonance. Let's do another example. Here we have OCN. Notice that each possible Lewis dot diagram follows the octet rule. So which one is the better Lewis dot diagram? So first we got to figure out the formal charge of each atom. Take a moment to do that. Here are the formal charges of each atom. By looking at the formal charges, we can see that the dirt Lewis structure is the worst out of the three. So on the exam, you can pick either one, it'll be fine. Scientists have done quantum mechanics calculation to determine which of these Lewis dot diagrams is better. It turns out the first one is much better than the second one. So why would that be the case? Why is that one more favorable? If you think about it, the negative formal charge is on the oxygen, while here the negative formal charge is on the nitrogen. The oxygen is more electronegative than the nitrogen, so it's more likely for the oxygen to have the negative charge than nitrogen. In practice number 1, I want you to find the formal charge of each element in the following substances. Pause the video and resume once you complete it. Okay, so here's the answers. For number 13, here we have two resonance structures of the sulfate ion, which is a better Lewis dot diagram. So to figure this out, we must first indicate the formal charge of each atom. So notice that the second one has more neutral formal charges. Therefore, it is the better one. For number 14, we have the diocyanide ion. We have three resonance structures of the ion. Which one is a better Lewis dot diagram? So the best one is the one with the most neutral charges. So if we indicate the formal charges, we can see that the dirt one is the worst one out of the three. So the first two are acceptable. For 15, we have three possible resonance structures of OCS. Which one is the best Lewis dot diagram? By indicating the formal charge of each atom, we can see it is the first Lewis dot diagram that is the best one. For number 16, if we indicate the formal charges, we can see the first Lewis dot diagram is the best. So I am going to go over more details about resonance. Not all molecules have resonance structures, but if a molecule has resonance structure, each of those resonance structure represents that molecule. There might be one of the resonance structure that's more favorable than the others, but all those Lewis dot diagrams represents the substance in some degree. For example, here we have a resonance structure of benzene. Are these the same substance? The answer is yes. These two Lewis dot diagrams are not isomers of each other. If they were isomers, then there would be a different substance, but these are resonance structures of each other. So they are referring to the same substance, which is benzene. The reason why both of these Lewis dot diagrams represent the same substance because sometimes it's very difficult to draw just one Lewis dot diagram for one substance because electrons can move around in the molecule. So the electrons are not just sitting in the bond or in the atom, they can actually move around within the molecule. So in a molecule that has resonance, the electrons are delocalized. That means they're not localized within a bond or an atom, but they can move around within the molecule. Therefore, you cannot express the molecule as one Lewis dot diagram because the electrons are moving. So here's an example of that. So the electrons are moving within the ring of benzene. As a result, the carbon-carbon bond is actually the same length within benzene. Even though if you look at the Lewis dot diagram, it has a double and single bond, and you know the double bond is shorter than a single bond, but because of resonance, each carbon-carbon bond is actually the same length. So it's not exactly a single bond or a double bond, but somewhere in between. So sometimes people draw the Lewis dot diagram of resonant compounds using dashed lines instead of a full bond. To identify if your molecule have resonance or not is usually molecules with lone pairs or double bonds or triple bonds have resonance structures. So the real structure is often a mix between the resonance structure because it is difficult to draw the actual Lewis dot diagram with the electrons moving around within the molecule. So sometimes people draw benzene as a hexagon with a circle in the middle to indicate the resonance. Some molecules with resonance structures have delocalized electrons, which means the electrons can move. And if the electrons can move, they can conduct electricity. So graphite on your pencil can conduct electricity. I'll show this in class. So if you look at graphite, it basically has resonance because of a double bond. In a sheet of graphite, there's lots of double bonds, so there's lots of possible resonance structures. So electrons can move from one sheet of graphite to another sheet of graphite. Even though graphite is made up of carbon, and carbon is a nonmetal, and we know nonmetals do not conduct electricity, but because graphite has resonance, it can conduct electricity. So people have used graphite as a semiconductor in phones and electronics because it is a cheap alternative to expensive metals. Learning check number 8. All the following are resonance structures for NO3- except for what? Pause the video and resume once you complete it. So the answer is choice 3. If you compare choice 3 with the other choices, it has extra electrons. It has 2 extra electrons. In resonance structures, electrons move around within the molecule. You do not add or take away any electrons. For the last practice, I want you to draw possible resonance structures of the following and note the formal charges. Pause the video and resume once you complete it. Okay, so here's the answers. So this concludes the video lesson for today. Remember to do the Junipod homework.